here I have 3 samples that were made in my lab of organic molecules dissolved in solvent. If I shine UV light through them, they give off a very beautiful color. And this phenomenon is known as fluorescence. And you'll learn about fluorescence in IB chemistry. So these are types of dyes. Okay. But in paper 3 of the IB chemistry exam, you'll have to choose an option, and one option is option B, which is human biochemistry. And one subtopic is pigments. And these pigments, similar to these dyes, they absorb light and re-emit light. So they give off some color. So one commonly studied type of pigment in the IB syllabus is anthocyanine. Anthocyanines, first of all, are deemed aromatic. They're aromatic because they contain these cyclic carbon rings containing double bonds. These double bonds are known as alkene functional groups, and you'll learn about that in organic chemistry, part of the course. They're also water soluble because they contain polar groups called hydroxyls, these OH groups. And these hydroxyls are capable of undergoing a particular type of intermolecular force of attraction called hydrogen bonding. Hydrogen bonding is the interaction between electropositive atom, in this case hydrogen, electronegative atom, oxygen. Okay. So water molecule interacting with the hydroxyl group, allowing these molecules to solubilize or dissolve in water. Okay, so they're water soluble. Like dissolves like, this is the rule. So this is the structure of a particular anthocyanine known as cyanidine. Cyanidine is a particular pigment you'll find in many plants, for example poppies, and also cornflower. So if we have this pigment exposed to an acidic environment, when I say acidic I mean the pH level is relatively low or below pH 7, then it's going to have this particular structure, okay? And it will absorb light, it will absorb blue-green light in the visible region of the spectrum. And when this molecule absorbs blue-green light, it will emit the complementary color. So the color that we see is the complementary color that it actually absorbs. So it absorbs blue-green light, so it re-emits red light. And we can demonstrate this with this energy level diagram. Delta E just means the change in energy. So initially absorbing blue-green light, and then it's re-emitting red light, okay? And this energy gap is relatively large, okay? But if we expose this molecule to a more alkaline environment, when I say alkaline I mean the pH is increased, it now switches. Now it absorbs red-orange light and then re-emits blue light. And that's because we've increased the conjugation of this system. We've actually got a higher number of double bonds. So now we have an additional, it's changed, we have an additional double bond between the carbon atom and the oxygen atom that was initially a hydroxide. And this is actually increasing the delocalization of pi electrons throughout this molecular system. Okay, pi electrons are just the electrons involved in forming double bonds, or alkenes. Okay, so again, using the energy level diagram, we can show that it's absorbing red-orange light. Now this energy band is actually decreased in size, so it's easier for this molecule to absorb a higher range of the wavelength of visible light. Okay, so it absorbs more visible light. And now it gives off blue color, so it gives off the complementary color. So this is like the basis of how pigments release light in IB chemistry. This is some of the key details that you need to understand about pigments.